Hey guys, on behalf of Submarine Team 1B, I'd like to welcome you to our design presentation. Today we're going to show you the submarine ballast system we designed. I hope you enjoy the show. So today we'll be going through how we went about designing the submarine ballast system. So mainly with respect to the functionality, we'll go over how we achieve surfacing and freeboard, fine buoyancy control, pitch control, and then for emergency situations, how we use the drop weights and emergency MBT deballasting to get the passengers to the surface as quickly and safely as possible. As for the project requirements, as some of you might know, we were tasked with designing a ballast system that was capable of withstanding subsea pressures up to 1,000 meters, main ballast tanks used for surfacing capable of generating 2,200 kilograms of buoyancy, variable ballast tanks for both trim and depth control, providing a maximum of 50 kilograms in buoyancy, and finally a drop weight mechanism for emergency deballasting. Surfacing the submarine and achieving a freeboard large enough so that the sub can be successfully loaded and unloaded is achieved with two main ballast tanks, or MBTs. At the beginning of each dive, the two MBTs are filled with air, allowing the sub to be in a positively buoyant state and remain above the water. In order to begin the dive, the sub must enter a neutrally buoyant state. This is accomplished by opening 4 solenoid-controlled air vent valves located on top of each MBT. As air rushes out of these vent valves, flood holes located on the underside of the MBTs allow water to rush inside and vent the MBTs of air. With the MBTs vented of air, the submarine is in a neutrally buoyant state and can begin its dive. At the end of each dive, when the submarine is a few meters below the surface, the 4 air vent valves are closed. Onboard air stored in 4 high-pressure air cylinders is used to purge the MBTs of water. The high-pressure feed line connected to the air cylinders first passes through a differential pressure regulator. This is used to ensure that the air entering the MBTs is kept at a pressure 200 kilopascals above the ambient sea pressure at any depth. Next, a solenoid valve, normally kept closed throughout the dive, is opened, allowing air to enter the feed lines connected to the MBTs. As air enters the MBTs, the water inside of them is forced out through the flood holes. When the MBTs are completely purged of water, the sub is now in a positively buoyant state and begins to surface.
The hydraulic circuit allows depth control and pitching control at neutral buoyancy. The capacity of the rear VBT is 25 kg and the capacity of the two front VBT is 12.5 kg. Thus, we have a total buoyancy of 50 kg. The depth control circuit open to the sea is composed essentially of 4 solenoid valves controlled electromechanically by the pilot to control the flow of the water. A swash piston plate pump connected to an electric motor with an angular speed of 1,800 RPM, a safety valve to prevent overpressure of the pump, and a check valve to provide back pressure surge protection. For descent, water is pumped from the sea to the 3 VBTs. The quantity of water between 25 and 50 kg depends on the desired speed. And for ascent, water is pumped out of the tank to the sea. At neutral buoyancy, all the variable ballast tanks are at their half capacity, which means 12.5 kg in the rear VBT and 6.25 kg in the two front VBT. Thus, the normal speed, ascent and descent depend on the quantity of the water in the VBT. The minimal speed is 0.4 meters per second and the maximal is 0.5 meter per second. The pitching control circuit is a hydraulic circuit close to the sea, composed essentially of 4 solenoid valves and the same swash piston plate pump. For negative pitching, all the water from the two front VBT is pumped to the rear VBT, and for positive pitching, all the water from the rear VBT is pumped to the two front VBT equally. This is giving us a maximal angle of 1.49 degree. It depends on the overall buoyancy of the variable ballast tanks.
Now comes a very critical question. How safe is a ride with our submarine? To make sure we have a solid answer for that question, we implemented two independent safety procedures. The first one is the drop weights currently shown in the animation. It is composed of 250 kilograms of the submarine's main batteries, alongside with lead weights added to both ends of the cylinders as needed. The drop weights are attached to a submarine using three normally extended solenoid actuators that are attached to three collars, which encapsulates the body of the drop weights. They can be released either by a direct signal from the pilot or automatically released upon power outage. The main design concept of the drop weights is to ensure that the submarine is heavy enough to allow neutral buoyancy to be hit using only the capacity of the VBTs as discussed earlier. In other words, when the weights are dropped, the submarine is guaranteed to be positively buoyant and thus jettisoned to the surface. To give you an idea, the average ascent time of the submarine relying only on the drop weights without the use of the thrusters or the VBTs from a depth of 1,000 meters is just 13 minutes. The second safety measure is MBT's deballasting. The idea is very simple. Upon emergency, purge 10% of the MBTs with compressed air from the air bottles. The airflow is controlled using a solenoid valve. This breaks neutral buoyancy and thus the submarine starts moving upwards. However, as the sub moves up, the seawater ambient pressure decreases, which in turn expands the air inside the MBTs. To fix that issue, the pilot is required to vent air out of the MBTs as needed to keep the volume of the air inside the MBTs constant. To give you another idea, the average ascent time using MBTs deballasting only from the maximum depth of 1,000 meters is 20 minutes. In case of extreme emergencies, this can be combined with the previous measure of the drop weights procedure, decreasing the ascent time even further.
Now we can discuss the design changes that parameterization can allow. The user is allowed to enter 5 different inputs: the surface temperature, the selected ocean, for example Pacific Atlantic Ocean with its specific salinity, desired ascent and descent speed, minimum desired freeboard, and maximum operating depth. The outputs are structural changes on the MBTs, VBTs, and drop weights, as well as the number of air bottles. The flow chart on this slide is a summary of the logic behind parameterization. For example, if the user chooses a combination of temperature and salinity, it would be affecting the buoyancy of the submarine because it's affecting the density of water. By choosing a maximum operating depth, this affects the thickness of the VBTs and the number of air bottles needed to deballast the MBTs. So the higher the depth, the thicker the walls, and the more air bottles needed to deballast the MBTs. In order to control the ascent and descent speed, the height of water inside the VBTs need to be either increased or decreased. The maximum speed that can be achieved by the VBTs is around 0.4 to 0.5 meters per second, while only using a sixth of the full power of the thrusters. And finally, we can compute the mass of drop weights by computing the dry mass of the submarine and its total buoyancy. And we can also compute the freeboard of this optimized submarine and compare it to the desired freeboard of the user. If it's lower than the minimum desired freeboard, the algorithm loops back to increase the radius of the MBTs and achieve the desired freeboard. These two pictures over here are two examples of extreme parameterization. The first one is at a maximum operating depth and is achieving a high freeboard. This is why the radius of the MBTs is large and the number of air bottles are 4. And the second one is the opposite conditions with minimum depth of 330 and minimum freeboard. However, the drop weights are heavier because the submarine is lighter and more weight is needed to bring the submarine to neutral buoyancy.
So to wrap everything up, We ensure efficiency by ensuring that the submarine is capable of ascending and descending using the ballast systems only. We ensure simplicity by only purging the MBTs 50 meters close to the surface and using only one pump to facilitate both depth control and pitching. And then we ensure safety by implementing two independent safety procedures, i.e. the drop weights and MBT deballasting. Thank you.